morning to all of you. Our topic for today is about the pH diagram of the vapor compression cycle. So again, I'm Engineer Charlton as in your teacher in refrigeration engineering. So before we move on, we have the learning objectives, and these are the following. No, so the first to familiarize and interpret the parts of the pH diagram. And number two, to relate the vapor compression cycle of refrigeration system with the pH diagram. So first, now we have here the vapor compression cycle on the left side and the pH diagram at the right side. This is the pH diagram. By the way, the pH stands for pressure, the P, and enthalpy, the H, now as designated by the variable H. So first, we have to interpret the diagram, and then we relate to the vapor compression cycle, as can be seen on the left. No. So first, how to construct a pH diagram? No, so or the interpretation of the pH diagram. So if you can see this dome, if you can see this dome, no, so that is the familiar form of the pH diagram, no, wherein the enthalpy and the pressure are being plotted, no, depending on the other parameters like the temperature and the other parameters. So what is important here is this. Now you can divide the diagram into two parts, left side and the right side. So on the left side, this one, no, is the saturated liquid line, and the other part is the saturated vapor line. No. So what is the meaning of that? So the meaning of that is the condition or the state of the refrigerant as the working medium in the cycle. So here it is pure liquid. No, and the parameters here can be seen with this F subscript: entropy of fluid, volume of fluid, enthalpy of the fluid, like that. Now here, the condition here is the saturated vapor or gas. So uh, the then the subscript here is in G. Now, entropy of gas, diba? Volume of gas, enthalpy of gas, and so on and so on. Okay. So meaning here is pure liquid. Here, from here is pure vapor, 100% dry. This is 100% wet. What about in the middle? The middle is the mixture of liquid and mixture of vapor. And it can be interpreted with the variable X, the so-called quality, no? The quality of the refrigerant, no? In terms of dryness. No? So the other term for the quality is dryness fraction. So intuitively, when you reach the half, it could be 50%, no? And then 75, 98, 99 um, dry, no? Because we need a dry, saturated refrigerant, and then we need to heat it to improve the efficiency, and you will fall in this region, which is the so-called superheated. Okay, so let me change the color so that it will. So this region, now we are now in the region. So this one is super heated, meaning a region where it is above the the saturation point. So this is the saturation point. Beyond that is super heated, meaning a lot higher in temperature and pressure than in saturated. So this one is saturated liquid. Beyond that is the subcooled. What about this at the middle? This is the critical point. Yeah, critical point wherein you can no longer identify whether it is liquid or a vapor. So this is the critical point. Now we go to the one is to one correspondence of the vapor compression system, which is the most popular system in the refrigeration, and how does it relate to the pH diagram. So here, this line, it has an interpretation of this line 4 to 1. The equipment here is the evaporator. So you can see the pressure in the evaporator is low. And if the pressure is low, the temperature is low. No, that is according to ideal gas law. So here at the top, now corresponding to the evaporator, now at the opposite of the evaporator is the condenser. Yeah. So if I may relate, so this is evaporator, this one. No. So what is happening in the evaporator is we are adding heat, QA, heat absorbed or heat added. Yeah. Between the evaporator and condenser, the evaporator has the cooler or colder part, lower temperature part. So this one is the condenser. This one is the condenser. So this line is the condenser. Yeah. So as you can see, the pressure is high. Therefore, the temperature is high also. So we call this temperature, this side as the high side. This is the high side of the refrigeration system, and this is the low side. What about the other two? Here is the curve here is the compressor, yeah, where the work is happening. So among the equipment, only one produces the work, the actual mechanical work. That is the compression, work of compression. And what is happening there is the isentropic compression, no compressor. And the last one is the expansion valve, which is here. This is the expansion valve. Okay, expansion valve. So that is the parts of the refrigeration system. So to recap, this is the evaporator. Sorry, the evaporator, the low side. This is the condenser, the high side. This is the expansion valve. It reduces the pressure from the exit of the condenser down to the entrance of the evaporator. So this one is isenthalpic, meaning the thermodynamic process that happening here is the enthalpy is constant. As you can see here now, enthalpy is constant because it is straight line. So the pressure is going down, going down, but the enthalpy remains the same. No, the pressure is going down, enthalpy is remaining the same. So that is constant enthalpy, but the pressure is lowering down. So that's the purpose of the expansion valve. Opposite of the compressor, compressor is you are trying to increase the pressure. When you increase the pressure, you compress the gas. Now you press the gas, then the temperature also increases. Okay, so this one, the pressure is going high. Here, the pressure is going low, so that the evaporator can only accept low pressure and low temperature. What about this? The condenser, the evaporator is absorbing heat from the surroundings, from the people, from the water, from the vegetables, everything that it needs to absorb, no, so that it can have a cooling effect. So cooling effect is happening in the evaporator, absorbing heat, while the condenser is discharging heat. No, that's why Q is heat, subscript R is R, rejected. No, heat reject. So what's happening in condenser? It rejects heat so that it can produce condensate. When you remove heat, it will the surroundings or the medium can be cooled. So when it's cooled, and then it can be transformed to liquid refrigerant again. So here, when it's cooled, yeah. So here is the saturated liquid. Now this one is saturated vapor. This one is superheated vapor. So these are the one is to one correspondence of the vapor compression system and the pressure enthalpy diagram. So it's kind of intuitive, so that when you see the pressure enthalpy, you would you can interpret what is happening in the vapor compression system. Now, it is not only pH diagram that is being used in the representation of refrigeration. You can also use TS. No, this is the so-called TS diagram. T means temperature, and S stands for entropy. No? But the most common way to represent the refrigeration cycle is by pressure and enthalpy because it's the formula is based on those diagram now. But we can interpret also this now. So for example, 1 to 2, as I said, no, what is happening in the compressor, you can experience the isentropic compression. Okay, so here you cannot see a straight line here because there's no entropy, but here there's an entropy. So here, no, a straight line here, a straight line here, meaning you are having a constant entropy, a constant entropy. The temperature is increasing. How do you know that the temperature is increasing? Because from 1 to 2, the direction is going upward. So look at this. Yeah. From 1 to 2, the temperature is increasing. Uh, and that is very obvious because from 1 to 2, you are compressing. So the temperature and is increasing from 1 to 2. And the pressure is also increasing. So here, entropy is constant. And you can see that in the TS, TS, because temperature is horizontal, but you can interpret this now. So these points, these points, these points are constant. Then here, I would like to emphasize that this is the condenser, and these are heat exchangers. No? So they are called heat exchangers. They allow heat to transfer, no, from one place to another, no, with two medium minimum. For example, the air and the refrigerant. So what's happening here in thermodynamic perspective? Here, the thermodynamic process is pressure is constant. Pressure is constant, and then this one enthalpy is constant. Okay. So again, entropy is constant, pressure is constant, pressure is constant, enthalpy is constant. So those things or those knowledge will help us to get the needed data from the thermodynamic tables if you know those properties. Because easily in this pH, you can identify three, now direct 3 points from the table. And what are those? So look at this. Let me with the pH diagram, you can easily identify three. Yeah. So look at this. Yeah. So here, this is saturated vapor. No. So for example, you can get the enthalpy of one, entropy of one. But here, you can get the enthalpy of two because entropy of one is equal to entropy of two, the constant. This is the isentropic line. Isentropic line. Now, this is straight here in TS, is the curve here in pH. So S1 equals S2 because they are isentropic. Okay. So in the steam table, you can get that. You can get this and also this. Yeah. Where's this? So here is the liquid line or wet. So you can get the SF, the HF, the internal volume F, saturated liquid. And so easily the three you can get. And then four you can get intuitively because this is constant. So H3 equals H4. No, because yeah, yeah. Because enthalpy is constant. That is it. This enthalpy is constant. It is not changing, although the pressure is decreasing. So H3 equals H. So the knowledge in the pH diagram would help you to really get all the necessary data from the refrigerant table, no, depending on the type of refrigerant, and then you can solve for the parameters that are being asked in refrigeration. So what are those? So for example, the refrigeration effect, which is the H1 minus H4, because the refrigeration effect is the cooling, the cooling capacity of the system. No, the evaporator is the one producing coldness. No, so the refrigeration effect is happening in the evaporator. So this one, and if you multiply
Sir,
this with the mass, then it will
Sorry,
give you the heat. Okay, ma'am?
sorry for interruption, sir. Opo.
Okay na po?
Para up na po, sir. Opo.